Thanks for being here already. Wilma? Yeah, why don't we discuss it? We can discuss that later, maybe after the presentation, all right? Let me know if the sound is coming through this time. Wilma, if you don't mind, let me know if you can hear me. My mic bar is fluttering away, looking like it's going. Loud and clear, perfect, awesome, thanks. Space audit's nice. Nice, excellent. Cool. That means we are set to go. Beautiful. Good. Just wait right till 8 o'clock, all right? And yes, Wilma, that is right. There is no radiative greenhouse effect. The concept does indeed violates all the laws of thermodynamics. First law too. What about greenhouse effect from insulation of the atmosphere? Well, that would be not the greenhouse effect as it's derived and shown. Um, yeah, insulation isn't the greenhouse effect, and it's not clear what it would do to insulate anything because it's a gas. Gases convect. Gases carry heat away in convection. Um, we'll see during the lecture that there's actually no possibility for excellent for any additional effects because we can explain everything just with basic laws of physics and ideal gas law type stuff. So there was no additional effect needed. There's no need to postulate a greenhouse effect. Here to learn, excellent. Ordo Gnosticus Illuminatio. I like the name. Illuminatio, that's awesome. Space audits, that sounds cool. Ordo Gnosticus Illuminatio. Yeah, just gonna wait till 8 o'clock so that everybody who's planning on it being for 8 can show up. I just wanted to get it going early to make sure the sound was working tonight. I'll explain once it's 8 o'clock and more people are on. I can tell you what happened last night with the headset. Watching from Oz, nice, excellent. What time is it there? Because it depends. Oz is pretty wide, isn't it? How many time zones does Oz have? I think there is a bit of a delay in my speech compared to what I see you guys chatting, just because I put it on high resolution, so it means there's a bit more latency. Um, just because I want the video recording, the recording of the stream to be high resolution for rewatching later, because there are quite a few slides with a lot of text. 2.5. Sorry, what's 2.5? That's the time, 2:30 a.m. Midday. Oh, perfect. Oh, they have 2.5. Yeah, okay, yeah, perfect. 2.5 time zones, right? Yeah, there should be at least one other person from Australia coming on that it was, well, that indicated he wanted to come on. Stephen Wells is a good character. Just gonna look at my pre-show, pre-lecture notes here. How I want to introduce this. Oh yeah, right. Okay, nice, good. Yeah, right. Rumors abounded of my demise. Yeah, sure. Yeah, gosh. Yeah, man, and my energy was so high because I had that ready to go since last weekend, and I was just like, oh man, I got to wait a whole week. My energy was just like so pumped and so ready for that last night. You got to be careful about stuff like that. You have to really, really, really pre-test it more than once. Pre-tested it a couple of times. Okay, looks like I got it working, and then when it comes to live performance, right? Malabi. Yes, I am Australian. Perfect. Okay, 5 more minutes on my end. Up to 14. Awesome. That's I'm getting there to what levels we were at last night. Good. Thanks. Ordo Gnosticus Illuminatio. Nice. Truth, beauty, goodness, love. Yes, and isn't that what we want to pursue, right? That's what I wrote about in Illuminism. What is our religion if we want to be an Illuminist? The pursuit of the form of the good. And what did I ask on my Facebook group? Is beauty a virtue? Sure, beauty is a virtue. The ancient Greeks certainly would have said beauty is a virtue. Why else would you create a beautiful marble sculpture? Because beauty is wonderful. Beauty is goodness. Beauty is truth, right? What caused a sound problem last night? Yeah, I'll tell you when more people get on. I'll tell you at 8 o'clock. Oh, good, Jopo. Nice to see you. Perfect. Virtues, yeah. Yeah, that's true. Yeah, love hasn't been covered at all. Yeah, nor compassion. Yeah, God, look, isn't that a genuine reaction? Nor compassion. Look at the reaction you got out of me that got out of me for that. Yeah, God. Yeah, compassion is not quite there, is it? But it's not surprising. Look at what's happened to Gnostics. They're burned at the stake. They're freaking flayed alive, skinned alive, and killed. The modern manifestation of that is the trolling and the multiple many attempts to destroy, ontological mathematics. People just writing books about philosophy. Oh, all the trolls come in and want to destroy you. So, yeah, I mean, the enemy isn't compassionate. Why would we extend compassion uh, to them? Uh, yeah, that was funny. That was good. Yeah, I know. Yeah, there's nothing worse than that going live and then some. Yeah, unforeseen difficulty. Yeah, I know. You probably saw it on my face. I was pretty upset. I was pretty mad at myself. We're not just fully, I mean, I did pre-test. I pre-tested a lot, and it was actually out of my control. I'll tell you what was wrong with the sound. Tell you in just a minute, just in case a couple more people log on here at 8 o'clock. By 8, I got 7:58 here, as you can see. But yeah, I would say it's pretty clear that the writers of, the Hockney writers, it's pretty male writing. I mean, we typically don't talk about love, at the base, um, male mind. I mean, love is a pretty simple sort of physical act. I mean, we shouldn't be so dumb. Obviously, men are capable of much more than that, but you know, thing is, we can get away with it. Um, yeah, one more minute, Boomy, for sure. T minus one. Yes, well, are you feminine? Ordo Gnosticus Illuminatio? You sound perhaps a little bit with the language you're using. Yeah, for sure. I had this dream the other night of I dreamt of Sophia. Well, I'm just putting it in the context of Sophia. What would be Sophia to me? I dreamt of, I was basically her anima in the dream, and holy God, yeah. Anyway, not that it was lewd or anything like that. It was just a very nice dream. The feminine, rational. Anyway, whatever. God, it's getting up on some crazy. Um, yeah. All right, here we are, 8 o'clock. All right, guys. So here is a 2.4 gigahertz receiver for my wireless headphones. And usually that stays with my gaming PC. And then I go on this laptop and I just use Bluetooth. Uh, the Bluetooth on my laptop just quit working last night and it doesn't work anymore. So, I mean, what a crazy, stupid coincidence, right? That right at that time is when the your alarm clock worked. Great, Philip. Right at that time is when the Bluetooth just stopped working completely on the laptop. That's why I remember I was turning the Bluetooth on and off a couple times, and you guys would hear it just for a sec, and then it would stop. So yeah, what a stupid thing. How annoying, right? All right. So I'm going to disappear the display, sorry, the video capture of me, and put on and start the slideshow. Okay. How does that sound? Good, you guys? And let's start this slideshow. Okay. Um, so I won't be able to watch the chat very closely while I'm giving a lot of these slides because all I can see is the slide. At a couple times I'll stop to ask a question. There is about a 20-second delay, it seems like. So I'll maybe give a minute if I think it'd be fun for you guys to answer a question. Okay. So first thing is, why is this lecture important? Why is it important? It's important because it demonstrates how to determine and think about the temperature of the Earth without this thing that the mainstream narrative calls a greenhouse effect, right? Because they always tell you, oh, the only way to explain the temperature of the Earth is with this greenhouse effect. No, I'll show you precisely how to do it entirely without any need for a greenhouse effect. This is important because it's this greenhouse effect idea, which is the basis for all of the climate policy. And what we will see is some really crazy and dangerous things that they want to do to geoengineer the Earth, which if you simply extrapolate where it looks like they're going, it's going to end up in an extinction event for all life on Earth, like a really bad big deal. It looks like they're scheming something, especially when I show you some of the conversations I've had. This will be after the main presentation. Some of the conversations I've had with scientists on this are really perplexing, right? So the first bit of this, probably the third of tonight, maybe the first half, is going to be the lecture proper. And then afterwards, we will have I'll present additional context via these slides and comparisons to the greenhouse effect method that they use, how it's derived, where it comes from, and what's wrong about it. Okay, great. All right, so Planetary Physics 201. Lecture 1, Earth's temperature. So why would this be a second level course? 201 basically means it's a second year course in um, in a university degree for astrophysics or physics. Now, why would it be second year? Because you actually have to integrate a lot of concepts that you would have learned in first year and that you would concurrently be learning in second year to actually solve this problem of Earth's temperature. Actually, it takes quite a bit of science. You have to get past the first year of physics in a university to be able to answer this question. It's about, at least when I was a student, a second year level question. Okay, so that's why and this was actually the course that I learned the Earth temperature, but it was via the greenhouse effect model. So now I'm giving you the lecture that I should have gotten on Earth's temperature instead of the lecture that I got with the greenhouse effect. So yeah, the name of my course was Planetary Physics. Might have been 201, but it was second year. I do remember that. Okay, so temperature. What would we like to know about planets as physicists and as astronomers? Let's try temperature because why not? There's lots of physics involved with temperature. And you know what, guys? Before we continue, I'm just going to switch over to the chat and make sure you guys can see this slide okay. So let me know if you're seeing this. And I'll switch over to the chat here. Okay, let me know that you guys were seeing those slides all right, that presentation. Hi, Carly. And that'll give me some sense of how long the delay is to chat with you guys too. Yeah, it's all fine. Okay, good. Thanks, you guys. All right, perfect, you guys. Thanks so much for that. All right, cool. Switch back. All right, what would we like to know about planets? Let's try temperature because why not? There's lots of physics involved with thinking about temperature. So this is a question I want to ask you guys first. Question to the class. What is Earth's temperature? Who can answer that? What is Earth's temperature? I would like to see some hands raised in class. Now just give me what you guys think. What is Earth's temperature? Who can say what Earth's temperature is? Who knows what Earth's temperature is? Let's see some values in there. Okay, Boomy puts in minus 18C. Anyone else? Boomy's the eager student. Boomy's the eager student, eh? Raising his hand right away. Average 15C at the surface. Bottom of ocean, it's 4 Celsius. Good, you know what? I like that I'm seeing a bunch of different values here. 50C, just a guess. Great, that's perfect. I'm glad that I'm seeing these values. You guys are doing awesome. Great. Oh, there's a few more. Yeah, minus 18, 288. Okay, perfect, you guys. Good stuff. All right, what is Earth's temperature? So plus 15C, minus 18C, plus 22C. These are all common answers, but none are strictly correct. Not strictly correct. Now, why not? It's because temperature is an intensive quantity. This is an important thing. It's not talked very much about in physics class, but we really should talk about it more. You do learn this concept in thermodynamics, but it's just, sort of mentioned in one class and then you move on from it. But temperature is an intensive value. That means that it has a value where you measure it. So what do you mean by that? That means that when you take the average temperature of a body that has a whole bunch of different temperatures all over it, it's not really that meaningful. You know, temperature has a value in the spot where you measure it, okay? So if you haven't, so it would only correspond to the temperature of a whole object if that whole object just so happened to have the same temperature throughout all of its parts. Then the average temperature would be the same temperature as the spot that you measured it. But that's a very, very unique case. In general, the temperature of a body is a bunch of different temperatures, and it really doesn't make sense to average them. Now, how can you think about that? I forget who gave me this analogy, but it's a great analogy. It works, and it's a bit, strikes home to everybody. So the average value is not meaningful. Think of the average number of testes and ovaries in a classroom where you have 50% girls and 50% boys. You can calculate it. What is the average number of testes and ovaries per person? Well, you get one testy and one ovary. So that's something you can calculate, right? Sure, you can calculate it, but does it make sense? No, it doesn't make sense, does it? Because it makes no sense that each person has one testy and one ovary, right? So it depends where you measure it. So you get that? Isn't that a neat analogy? So that's what's not meaningful about averaging everything. Not everything Not everything is mathematically meaningful to average, right? And temperature is one of those things, okay? It's kind of wonky to think about, but I mean, that's a good analogy, right? Um, and then I have gotten this sort of quote from a lot of scientists, and they're like, it's a real calculation, though. It's the real average. And it's like, well, what do you mean it's real? What does it mean it's real? It's a real calculation. It's the real average if every person in the classroom has to have one testy and one ovary. That doesn't make sense, right? That really doesn't make sense. Okay. Good. So just because you can compute it or say it, it does not necessarily mean anything at all. And this relates to Gödel's incompleteness theorem, which hopefully as a student you are learning about in your philosophy of logic course, which you are taking concurrently. And then also, of course, there's just lies. You can just lie and just say bullshit. That doesn't make any sense too, right? Gödel's incompleteness theorems are about undecidability. But you know, you kind of get that from lies. Maybe there's just a basic, I think maybe I've been confusing Gödel's incompleteness theorem with the basic concept of lies, or maybe there's some connection there. In any case, let's move on. So an example of an extensive quantity would be mass. Mass applies to the whole body. So your whole body has a mass, the whole earth has a mass, right? So that is a valid quantity that applies to the whole body, okay? Um, Now let's go to astronomy though. In astronomy, stars have a temperature. Okay, well, what have we just been talking about? We've been talking about how it doesn't make sense to have, for a whole body to have a single temperature. So how and why can a star have a temperature? How do we do that in astronomy? So no one has stuck a thermometer in a star, and the temperature is still always intensive. So how does a whole star have a single temperature? How do we do that in astronomy? You know, are stars uniform in temperature? You know, does a star have a single temperature, which explains and is found all over that whole body? No, stars aren't like that. Our sun is a star, and we know that our sun doesn't have such a temperature uniformity. It has all sorts of different temperatures all over it, especially when you go down in its atmosphere with depth, right? Atmosphere changes temperature. So what is the trick to get a star's temperature? Okay, because there is a little trick. So here's where we need to integrate a few concepts from first year. So we have Planck's law. Okay, Planck's law is the function of radiative intensity versus frequency or wavelength for a given temperature. So this is the black body equation as a function of frequency. Here's a black body equation as a function of wavelength. And you can see it's a fairly nasty looking equation. You know, you have an inverse of an exponential and then a -1 on the bottom. This, you know, how Planck solved this equation is the birthplace of quantum mechanics. It was Planck's solution, his derivation for the first time in history of this equation, which created quantum mechanics, as solving how to make this curve. They knew experimentally that you could get this curve. This curve is the Planck curve. It's a black body curve. It's basically the most efficient way that energy can be contained thermally in a body. It's basically what is representative. The most efficient packaging of energy, of thermal energy in a body is basically what this equation and this curve shows. That is a nice smooth curve. And yeah, so that's the most efficient way that energy can be packed inside a body. It was a big problem. They knew experimentally it looked like that, and they had all different equations trying to explain it that weren't working. And then yeah, Planck came up with the the quantum of action idea, H, and that's what solved the equation. Very fun, very cool stuff that you did in first year. So let's also think about what we learned about stars in first year. Stars emit somewhat like black bodies. So here's one type of star. This is actually our sun. That's kind of black body-ish. Not really. I mean, the front is somewhat of a black body rise. You know, if you look at the rise here, kind of steep, but also jumbly. And then down here, that's like a black body tail. Here's a star, kind of has the front, kind of has the tail, but bit of mess in the middle. Here's another type of star. All we know is that stars are kind of like black bodies, not very close, sometimes not very close, but you know, what are we doing in physics and in science? It's all we got. All we got are the equations we've solved and our observations. So how can we stick it together? You know, one more thing, Stefan-Boltzmann law. This is really fun. Stefan-Boltzmann law is the total power per unit area, the total power of a black body curve. So what it is it is the integral, right? So Wikipedia, where I copied this equation from, uses P. It said P for total power per unit area. Really should have used flux, because flux is joules per second per meter squared, or watts per meter squared. Really properly, you call that energy flux density, but we just call flux. But something really fun. Look at how nasty this equation is. You see that big, long, nasty equation, right? either one, either in terms of wavelength or in terms of frequency. You know what happens when you integrate this equation holding t constant and integrating either over frequency from 0 to infinity or wavelength from 0 to infinity? Analytically, you can do it. It's pretty hard to do. You can't do it until you're in second year calculus. You can't do it with first year calculus. You haven't learned enough calculus yet. But in second year university, you are getting to the point where you've learned enough calculus to know how to solve this equation. So look at that nasty equation. What does it come out to? It comes out to just something so beautifully simple. Sigma t to the fourth. Sigma is the Stefan-Boltzmann constant, and t to the fourth. And that's what gives you the total area under the curve. The total area under the curve being the total power. Okay, neat. So, and that's a temperature, and that is a proportionality, sigma, to temperature, directly to temperature. So let's define something. This is what we do in astronomy. We define this thing that we call effective temperature. And the effective temperature is the temperature at which a black body would emit if it emitted the same total flux as the integrated stellar spectrum. So what that means is you use some sort of interpolating scheme to interpolate through all these points and then just do a numerical integration to get that total area. So that'd be your observed total area, total power underneath all these black dots, right? So your total power there. That's your F, and you equate that to sigma t to the fourth, and obviously then just solve for the effective temperature, right? You divide by sigma and take the fourth root. That gives you effective temperature. So a couple things to note. This is not the actual temperature of the star. It's maybe a ballpark metric. You know, it's not the actual temperature of the star because the star is in a black body. That only works, this equation only works for a perfect black body. Stars aren't black bodies, but what the hell else do we have available, right? We don't have anything else available. We have these basic laws of physics we figured out, and we have some observations. Well, let's try to put it together, even though it's rough. I mean, this is empirical science then, right? We're going to try to put it together as best as we can, even though we know, well, it's not perfect, right? A star isn't a perfect black body. And so the temperature won't be actual, but it'll be some estimate, So strictly, it's a fictional temperature. It's fictional. It's probably close, somewhat close. In fact, it'll be too low because because a pure black body, a perfect, beautiful black body, that is the most efficient way to emit energy, and that means that it's actually the coolest way to emit energy. Anything that's not a black body is going to be actually a little bit warmer than what you calculate for the effective temperature. So you calculate the effective temperature, but that assumes a perfect black body. In real life, it's not a perfect black body, so that means that it's probably actually, if you could go and measure it, it would have a higher temperature than what you calculate. Okay, so this works well enough for what we call spectral classification, classifying stars by temperature. Okay. So now we're finally going to do some new science, Earth, and some second year science, Earth and effective temperature. Can we do that scheme, effective temperature for the Earth, like we do for stars? Well, why not? Earth has a spectrum. And in fact, we can solve from first principles what the effective temperature of the Earth is, because we know that the Earth, the only source of energy for the Earth is solar energy, and that the Earth really doesn't produce much of its own energy. It's negligible anyway. And so we can calculate the effective temperature that way. So this would be the scheme. You would say, given the sun's effective temperature, its distance from the Earth, and Earth's radius, use the cross-section of Earth to get the total absorbed solar energy. Factored for albedo, that means the portion of the solar light that Earth reflects away. And use that as Earth's output per average unit area of Earth's surface. So just like this. Here it would look like this. Here you have the Earth, here you have the day side. Here you have the cross section, so that's the cross section. That's the amount of sunlight that's intercepted, right? Because it's a cross section intercept. And then we know a bunch of things. So you'd have to be given the effective temperature of the sun. So that would be given to you. That's 5,778 Kelvin. The radius of the sun, the distance between the Earth and the sun, the Earth's radius. So there's a whole bunch of terms here. A whole lot of canceling happens, and it can be simplified to just this F sun, which is the flux of the sun at the distance of the Earth, the top of atmosphere solar flux, and that's 1,370 approximately watts per meter squared. And then, so that if that's F in, your F sun, then the F out from the Earth simply becomes that F sun times 1 minus alpha, where alpha is the albedo, the reflectivity, the portion that's thrown away, reflected, divided by 4. That 4 being this 4, which is the area of a sphere, right? Because the area of a sphere is 4 pi r squared, whereas the area of this disk intercept is this term here, just the pi r squared, right? So that's why that 4 stays in there. And you get this value for the effective temperature. The result is Earth's effective temperature is 255 Kelvin or minus 18 C from approximately 240 watts per meter squared. So that is Earth's effective temperature. Definitely is. It's been measured. You can calculate it from first principles, and I'm pretty sure that it's been very well confirmed by satellites, infrared satellites that measure Earth's radiative output. Okay, good. So that is the effective temperature of the Earth. That's its, black body, quote unquote, temperature, because Earth isn't really like a black body, but this temperature is somewhat representative. It's going to be close, right? Now, here's the next question for the audience. Should this be Earth's temperature everywhere? So we calculate this minus 18 degrees Celsius effective temperature. Should that be the temperature we find on the Earth everywhere? So you guys answer that question. Should that be the temperature we find everywhere on the Earth? Let me check the chat. Great comments I see there, you guys. Yeah, good. I like that. Of course not. No. Boomy sarcasm. Great. Oh my God, that means if we didn't have the green effect, we'd be at Snowball Earth. Yeah, that's such a great lead in. Perfect. Okay, good. Yeah, exactly, guys. Yeah, no, that is not. And we'll come back to that eventually. Okay. We'll come back to that later in comparison to what the greenhouse effect does and what it says. Okay, so the answer is, of course, no. Why not? So, well, because the Earth is heated on one side and it's rotating. The temperature is always changing on the surface. The temperature is never constant on the surface. I mean, gosh, there's morning, day, night. Temperature is always changing. The Earth is heated on one side. We also know that the atmospheric temperature changes with altitude due to the ideal gas law and gravity. It's warmest on the bottom. We'll get into this later. That if you've climbed up a mountain, you might know, or you might know from flying an airplane, you see the temperature report on the little screen that you're watching, that the air gets colder as you rise in altitude, go up in altitude, right? So yeah, no, there's all sorts of temperatures, different temperatures all the time, everywhere, right? The effective temperature, remember, strictly it is a fictional temperature, right? Averages don't really make sense, although, we kind of attempt this scheme, by relating things to say, well, if they were a black body, which they're not, but we do this thing, because what else can we do? All we have is the laws of physics, and that's all we can do. So yeah, not literal or physical. Earth is not a black body. Now, going back to stars and their photospheres, like their atmospheres, the effective temperature may be found physically somewhere within the photosphere or the atmosphere. It might be, but there's no guarantee it will be, but it might be, right? So this is just an example from a stellar atmosphere modeling textbook. It shows this is in optical depth, tau. That corresponds to physical depth. It's probably for the sun over the range of several hundreds of thousands of kilometers or something. But it just shows that, the sun has an effective temperature of 5,778. So that's about here on this log scale. So you come all the way across to here. So this would be where in the atmosphere, the sun's atmosphere, the effective temperature occurs. And that's just entirely coincidental, really. I mean, there's other reasons why it would be there, due to that you could figure out from modeling and heat flow from the core. But in any case, it occurs somewhere in the atmosphere, right? But it's not the whole atmosphere, right? And this is just a table of this curve. So 5733, that's pretty close to 5778, and that shows that that's occurring at an optical depth at 5,000 angstroms at minus 0.4. So that was about where we estimated. So it's somewhere, the effective temperature is somewhere in the atmosphere, but it doesn't represent the whole atmosphere, right? Why would it? I mean, that the atmosphere changes temperature with altitude, and you have to explain the reasons for that, right? And we'll get into that. Okay, so lapse rate. Now that's what we're going to do, okay? Lapse rate. Lapse rate refers to change in temperature with distance. Like a stellar photosphere in that plot we just saw, Earth's atmospheric temperature changes with altitude. With a stellar photosphere, what we do in stellar photosphere modeling is we apply this concept called local thermodynamic equilibrium at each infinitesimal layer, at each slice of layer, 2D layer, parallel with the ground, right? So an infinitesimal slice of atmosphere at each layer for modeling. So can we try that for the Earth too? Well, why not, right? With a few caveats though. In the case of a photosphere and a star, that photosphere is highly radially symmetric. Any given column of atmosphere of a star's photosphere is quite similar to any other. They're almost perfectly symmetric, right? And heat input is uniform coming from the core of the star underneath the photosphere, underneath the higher atmospheres, which we model, right? So there is a great deal of radial symmetry, so you can, apply this local thermodynamic equilibrium pretty well to stars and do really accurate stellar atmospheric modeling. There is no real radial symmetry on Earth, though, is there? Because the heat input from the sun on the surface of the Earth mainly, it's not uniform at all, either longitudinally or latitudinally or in time, is it, right? The heat is constantly changing on Earth. It's not at all uniform. Then, on the other hand, only the first few hundred meters of Earth's temperature, of Earth's atmosphere, it changes temperature. I think if you go up like 1 or 2 kilometers, the temperature is actually really stable, and so there's not much temperature change, and so maybe then you do get some radial symmetry. So, well, what the hell else can we do, right? This is empirical science. We have some laws that we know for perfect situations, but then we have our observed system, which is messy. But else can you do but try to apply the equations, right? So let's try local thermodynamic equilibrium for the Earth and see what happens anyway. So you would do that this way. You would say the energy for a parcel of air, the total internal thermal energy of a parcel of air would be its mass times its thermal capacity times its temperature plus its gravitational potential energy. So again, its mass times its strength of gravity times its height above the surface and then plus whatever offset constant is there. Uh, but then for local thermodynamic equilibrium at each infinitesimal layer, what you do is you take the differential of that because you want to take the differential because the differential is infinitesimals, right? So once you take the differential of that equation, now you're down to infinitesimals. So you take the full differential and you get du equals mCp. Those are constants. They do nothing. dt, temperature, that's the only one that changes. So dt means change in, right? And then mg, again, those are constants, and dh equals 0. So that's called the adiabatic collapse rate. That's how you solve the basic adiabatic collapse rate. And we give that term or that symbol gamma, just to simplify it, gamma, kind of like an inverted L. So that's dTdh, so you just solve for dTdh where all is equal to 0, and you just obviously see that you would solve minus G over Cp. And that's about minus 9.7 Kelvin per kilometer. Great. And we call that the dry lapse rate. However, there's a problem. That's too high. It's true for deserts, but it's not true on average. The measured average is minus 6.5 Kelvin per kilometer. So we're pretty far off, right? We applied some basic equations. This is what we get from it from first principles, but that's pretty far off the average, right? So we're missing something, right? We're missing something big. What you need is it's slowing down, right? Because so this is a pretty steep, you would call that a steep lapse rate, right? Almost minus 10 Kelvin per kilometer. You need to slow that down to minus 6.5 Kelvin per kilometers, right? So what would slow down the lapse rate? How would you do that? Well, we got to go to the first law of thermodynamics and ask, how does one affect or change temperature? So the first law of thermodynamics tells you how. Now, who can tell us in the chat what is the first law of thermodynamics? The first law of thermodynamics tells us how to change temperature, okay? And we need to change temperature because obviously we need to change that lapse rate. That lapse rate is all about temperature versus distance, right? So how do we affect that temperature inside that lapse rate? The first law of thermodynamics tells you how. I'm going to have it on the next line. I want to see if anyone can tell me and write down for me what is the first law of thermodynamics. Oh man, someone's got it already. Good job. Well, someone got the answer we're working towards, but maybe someone can write down the what is the first law of thermodynamics. Just going to watch the chat here for a sec, see if anyone wants to write it down for me. Yeah, it is. Energy must be conserved, but there's and that's a good one. That is good. There, that's the one that I wanted. Good job, you guys. Good job, Boomy. You copy pasting that, Boomy. Good job. I really like K Pritik 1024 is one. That's awesome. Yep, you're in physics class. Good job. Delta E equals Q plus W. Nice, keeping my head down. Nice. Yeah, good. Yeah, good orthognostic illuminatio. Yeah, perfect, guys. Nice. Um, yeah, so du equals Q plus W, and then that would be MCP dt. So that means how do you change? So if you change the energy, if you change the energy of a body, that's what du means, the energy inside a body. So if you change that energy, that's going to be equal to Q plus W, and that equals to the mass of the body times the thermal capacity of the body times the change in temperature of the body, right? That's what the first law of thermodynamics is about. Tells you how to change temperature. If you want to change the temperature of the body, get a dT in the body, you need to give it either Q, that means heat, or work. Okay, and then that will also correspond to a change in energy, and that's where you get this idea that of the law of conservation of energy, right? Because that's a conservation law as well. Perfect. So no work is occurring other than the gravity term, which we already accounted for. Therefore, Q. Any source of Q? Some smarty pants already had it. Q sun. Well, Q sun, heat from the sun only occurs at the bottom of the atmosphere, or it mainly only occurs at the bottom of the atmosphere. We need to affect the entire column because it was the entire column on average. That's minus 6.5 instead of minus 10 about, right? Nitrogen, N2. Does that have any heat? No. Oxygen, O2, does that do anything with heat? No. Argon? No. These are all the major constituents of the atmosphere. CO2, carbon dioxide, does that have any heat? No, it doesn't. I mean, people want to say it does, but no. Carbon dioxide does not produce any heat. It's not combusting, it's not burning, it's not releasing, liberating its own energy. It's just a passive molecule like all these other ones are. It's just sitting there, bouncing around, doing nothing, right? What are we missing? Well, I gave it away, right? Because I said minus 10 was the desert value, but that wasn't correct for the average value. Well, what's different between a desert and the average area? Of course, H2O, water, vapor, and its latent heat. So what's so special about water? At its latent heat phases, it releases thermal energy without changing temperature. That is so cool, right? Think of how cool of a substance that is. Anything else when it cools, when it sheds thermal energy, it cools, or when it gains thermal energy, it warms up in temperature, right? But latent water has these two phases, either at the freezing point and at the vapor point, where you can pump energy into it and it doesn't change temperature. You can pump thermal energy into it and it doesn't change temperature. It just sits there soaking up that energy, soaking up that energy. And these are the phase changes, right? So that happens at, consider an ice cube. An ice cube at some point, yeah, it'll be warming up from say minus 10, it'll get to zero, and it'll just stop, and you'll be pumping that energy in. It'll just sit there at zero, right? And it's like, whoa, what's happening to that energy? We're pumping all this energy into this ice cube is just sitting there, staying ice at 0C, even though we're pumping all this energy into it, and you know that it's absorbing it. Pretty cool, right? Well, what happens? All of a sudden it melts, right? Phase change, right? And so the same thing, obviously, with boiling water and getting vapor. Really cool, really amazing, right? That there's substances that do that. I mean, that's the whole base of life on Earth, basically, right? So this is the wet environmental lapse rate when you incorporate water vapor, and it's a very significant value. So this is the way you would calculate it. This would be given either in an assignment or perhaps in an exam for this course. So you have the concentration, the molar concentration, or the mass concentration of H2O vapor would be its volume concentration times the ratio of the molar mass of the H2O vapor over the total molar mass of the air. So uh, the 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 vapor concentration, or sorry, the volume concentration of H2O vapor is around 2.5%. Molar mass is 18.02 grams per mole, blah, blah, blah. Molar mass of air is that much. The mass of air at the surface, this is at the surface, at your average STP surface, 1.225 kilograms. Latent heat of vaporization. So look at this value, 2,257,000 joules per kilogram. That's a lot of energy, right? Latent heat, the amount of energy that the latent heat phases of H2O and its liquid and vaporous phases, It takes a lot. Like it actually takes a lot. That is a very, very big value, 2 million joules per kilogram. So there's a tremendous amount of heat sitting in those latent heat phases. You think that's going to have an effect? The last thing to know is that the H2O concentration of H2O vapor goes from the value that you calculate here to 0 at 10 kilometers. So you do the math. You do the math by getting the total um, latent heat available at the surface, and then you split that out over the 10 kilometers just evenly because you're making an average, right? As that air parcel rises, it cools, and the cooling allows that latent heat to come out of the water vapor, right? So you do the calculation. What do you get? You calculate the rate of heat loss per meter or per kilometer from latent heat release, and you get gamma equals minus 6.24 Kelvin per kilometer after factoring into the minus 9.87 Kelvin kilometer per result from previous. Wow. Why wow? Because that's really close, right? Considering we assumed a local thermodynamic equilibrium to get this calculation, but the system is not really at all in local thermal equilibrium, especially near the surface where the heat flow is changing all the time, daytime, morning, nighttime, right? It's always changing. So considering that we're probably not really close to LTE, but we use this math and we get this result. That's pretty damn close, right? That's awesome. That's really satisfying, don't you think? Yeah, so if you want to do that in the exam, I'll give that as an exam question. Not really, but it would be. So this kind of indicates that there's no really other major temperature modulating factors at work. There's probably no other work or heat that we can really think of. If there were, like when we calculated the dry rate, we wouldn't get a close answer. We're getting a very close answer given the assumptions that we're making. No other major factors, or they all cancel. But then, what would they be? You need either heat or work. Well, there's gravity, that's work, and there's heat from latent heat. I mean, ponder on it all year long. Try to think of another source of heat. I can't. Well, actually, here's one. So the sun. So it is a good point, actually, that one reason why we're not near LTE or not exactly at LTE, local thermodynamic equilibrium, is that solar heat is being absorbed at the surface, and then there is some heat being absorbed directly by the atmosphere from the sun. So the atmosphere does directly absorb a small fraction of heat directly from the sun. And so that's actually going to be preferential because the atmosphere gets thicker at the bottom. So that means there's going to be preferential absorption of solar heat directly in the atmosphere near the bottom, right? And there would be less at the top. Well, think of that. There's more absorption, there's preferential absorption of solar heat directly by the atmosphere near the bottom of the atmosphere and less at the top. Well, what's that going to do? That explains perfectly. That fits right in to this discrepancy because that would actually steepen the slope. So we get this minus 6.24 from first principles, assuming LTE, but really there's a bit of heat coming in directly from the sun, preferentially at the bottom of the atmosphere. So that's actually going to steepen the slope for us a little bit, isn't it? And then maybe that would explain why we're a little bit low in that calculation. Does that work nice? That really works nice. We're really explaining things here, aren't we, with physics? Yeah, and of course, maybe there's a bit of rounding error. Another factor is the heat capacity and the latent heat of vaporization values. Those aren't quite constant with temperature, so you'd have to do a proper integral, really integrating over all these values changing with temperature, and that might change the results. In any case, we're pretty damn close, aren't we? Now let's get the atmospheric profile. Let's integrate gamma, the lapse rate, which is dt over dt by dh, which had this value, minus 6.5 Kelvin per kilometer, right? So you integrate that equation, you get this. Temperature as a function of height is minus 6.5 Kelvin per kilometer times h minus h naught plus t naught. So these are the constants that you have to insert. As you know, when you integrate an equation, you need to provide the constants. Well, the constants would be these terms, because when you differentiate, if you were to differentiate t now by h, that t naught constant would drop out. This h naught constant would drop out, and this h would just go to 1, giving you back the minus 6.5. Okay, so that's the integral. Question now is, what is h naught and t naught? So these are like anchor points. These are the constant value anchor points in the equation. H naught is some height in the atmosphere, some altitude, and t naught is some temperature. And T naught would be the temperature at some H naught. We got to figure out, what are we going to use? Where's the anchor point going to be? What is the height that we're going to use, and what is the temperature going to be there. We need those constants. What can we use for that? Well, why not use T naught as the effective temperature? Because what else do we have to use, right? So let's use the effective temperature for that T naught. That can be minus 18C. And we know from observation that that temperature occurs in the atmosphere at a height of 5 kilometers. Okay, so now if we plug that in and calculate T0, so we want the temperature at the bottom of the atmosphere, so that would be put in 0 there, right? So T0, T temperature at the bottom of the atmosphere, you plug in all the values, and what do you get? 14.5 degrees Celsius, and that's compared to 15 degrees Celsius observed. Now that is really awesome. So of course I discussed, why there's going to be a little bit of experimental error here. There's a lot of room for experimental error because, well, for all the reasons discussed previously, if you put that in Kelvin, if you put those values in Kelvin, this works out, and that's what you would need to do because obviously Celsius is an offset a little bit. Kelvin is an absolute scale starting at 0, right? Where 0 is actually 0. Anyway, it works out to a 0.3% error. That's pretty damn good, don't you think? 0.3% error, that's well within experimental error, especially that we're assuming for the average part that it's local thermodynamic equilibrium, especially where we're using this effective temperature, which isn't, quite really a temperature that should apply to the Earth because Earth isn't a black body, but like we said, it's going to be a pretty rough calculation. It's amazing that it works out as well as it does. So here we have just got the temperature of the Earth, the temperature at the surface of the Earth, that is, to 0.3% errors. Why is there another reason for discrepancy? Well, the heat from the sun occurs at the surface, so that's going to push the surface temperature a little bit higher, right? Because all this analysis assumes local thermodynamic equilibrium and some nice static system, right? But the Earth is not static, and one thing that pushes the system out of thermal equilibrium is that the heat from the sun is occurring mainly at the surface. So what's that going to do? That's going to push your surface temperature higher since that's where the heat is being deposited in the first place, right? Latent heat of freezing and vaporization, that's also going to keep the surface temperature higher because at nighttime, when there's cooling, a humid night cools less than a dry night, right? Because this water vapor thing, so that's going to prevent it dropping, you'll only drop to 0 Celsius instead of dropping to say -5 or -10. The water vapor there stops it from cooling as much. So that's going to push your net average that you measure globally a little bit higher. So there's lots of reasons why our calculated value is just a little bit lower, right? Lots of reasons that you can justify, and given that, like I said, it's still in a 0.3% error. Not really in thermal equilibrium or black body, but remember, we're using this black body temperature. Remember, black body is the lowest temperature for a given F. If your F isn't a perfect black body, if the spectrum of F isn't a perfect black body, if it has some non-unitary emissivity, then the actual temperature is going to be a little bit higher. But we're doing pretty well here. We've explained it, the temperature profile fully explained. And let's get into H naught, why H naught can be explained by the ideal gas law. So ideal gas law and H naught, so remember ideal gas law, PV equals NKT. So P, pressure, that's going to be set by Earth's gravity, right? Higher Earth gravity would be higher pressure, lower Earth gravity would be lower P, right? So P is a function of Earth's gravity. Is this back on? Yeah, okay, good. For some reason, this thing went to sleep. Okay, looks like my bars are fluttering. Just going to look at your comments for a sec. Nature math is beautiful. Nice. Latent heat, yeah. Good. Yeah, I know you want to see me, but if I put the camera in the way, it'll be in the way. I will put myself back on later. I can't keep track easily where I am in the view because I only show up in this view. So I can't tell what I would be covering up when I'm looking at the slides. I know, sorry. I'll put myself back on later when we can chat, okay? Okay, good. Well, my mic bar says it's fluttering. So yeah, I think my headset just turned off. I'll just wait a sec to make sure you guys say you can hear me. You guys are still hearing me, yeah? Does anyone let me know? My mic bar, as you can see, says, okay, I'm good. All right, thanks, guys. All right, perfect. Okay, so volume is set by Earth size. An atmospheric shell is, a function of Earth's radius. If you had a larger Earth, it'd be a larger atmospheric shell, larger volume, right? A smaller Earth radius, then you'd have a smaller volume. Okay, so V is a function of Earth's radius. N is set by the amount, the simple basic amount, the total mass of your atmosphere, right? So what's left? Well, K is a constant. What's left is T. T is going to be the independent variable, which gets determined from how the rest of these things are set by the properties of the Earth and the atmosphere, right? So it's simply going to occur where it has to by the ideal gas law, right? And one thing to note is that other planets, uh, even on the gas giants where you have one Earth atmosphere, you actually have the same temperature or very similar temperature as on the Earth at one atmosphere, right? So that's kind of neat. It just shows you that it's really just a function of the ideal gas law working, right? So H naught for T naught cannot occur at Earth's surface. You get this a lot from the greenhouse people. They say that T naught and H naught should occur at the surface, but it really cannot. One of the reasons which we've already discussed being that solar heat occurs at the surface. The solar heating occurs at the surface. Therefore, the surface has to be the hottest part, right? But of course, they don't get the solar heating, as we'll see later. They don't get the solar heating right in the first place at all. So the solar heating occurs at the surface, therefore that's where the hottest temperature is going to be. So you can't expect the average temperature to be where the hottest temperature already has to be because it's where the heating is happening. We have this lapse rate as we just derived, and the lapse rate necessitates it's a fundamental result that the atmosphere has to have a temperature distribution with altitude that has to exist due to gravity and the ideal gas law. And the result is that the bottom has to be the warmest part. The bottom of the atmosphere has to be the warmest part. If it has to be the warmest part, that means that it can't be the average part, can it? Right? That can't be where the average is, right? If it's the hottest part, that can't be there for the average part because the average occurs between the hottest and the coolest, right? Yes, the expected average by definition occurs around the middle of the sequence. Yeah, I bet you guys really do want to see me like looking at me. Okay, here I'll just stick myself up in the corner small, okay? And hopefully it doesn't get too much in the way. Okay, I'm gonna try not to take up too much room though, okay? All right, cool guys. Back to it. Okay. Yeah, good. Okay, lapse rate and where H naught T naught occur. Perfect. Okay, so now we're going to combine all this into a budget. Now, for your exam, I'm going to want you to memorize this. You don't have to memorize the words exactly. I just want you to be able to show me this in the exam that you comprehend how the Earth absorbs energy from the sun and how you get the effective temperature and what the sort of distributions you have to expect due to the basic laws of physics about the atmosphere, right? So, in this budget, heat flows one way. That's a very important concept you would have learned in your thermodynamics class in second year. Heat flows one way only, hot to cold. Heat comes from the sun, right? What is the solar heat? It's this value, 1370 watts per meter squared, which is an equivalent temperature of plus 121 degrees Celsius. I didn't discuss that much before when we derived this, but that's really warm, right? And then you use the Stefan-Boltzmann law, of course, F equals sigma T to the fourth. So you just solve for the T given this F, and that's the temperature. So that's the temperature of sunlight at the top of the atmosphere when sunlight is coming into the Earth, right? So really hot, right? The temperature of the sunlight is actually really quite warm. So what would you identify immediately in a diagram like this? Well, you would be able to identify that solar heat creates and sustains the climate, right? That's sensible, isn't it? It's sensible to think and to be led to believe that the solar heat is what creates the climate. That's pretty valuable scientific knowledge, I would say. And I bet some of you are just laughing right now because you know where I'm going to go with that. Um, yeah, if the sunlight is plus 121 degrees Celsius, well, that's hot. That's hot enough to melt an ice cube, to say the least. It's also hot enough to evaporate water, isn't it? Right? Well, that's going to create clouds. Well, gee, there's a lot of climate, and that, well, that's going to explain why the equator is so hot, right? It starts explaining a lot of stuff, actually, right? Um, and then, of course, the spherical average output is this minus 18C. That's the effective temperature. And then here I did, some sort of shading, so showing an atmosphere, warmer at the bottom, coolest at the top. Average has to be around the middle. This shows just the simple, because it's so simple to show the dry adiabatic gradient derivation. But, I have the remarks here. Account for water vapor latent heat release. That gets you the confirmed measured lapse rate, and there's no greenhouse enhancement. You just get the lapse rate as it is, and there's no greenhouse effect. If there was a greenhouse effect thing, the lapse rate couldn't be what it is, because like when we did the calculation with the dry rate and we found that we were way off from average, there was a reason, right? And that reason was because we had not accounted for something yet, and that's something we didn't account for yet was latent heat from water vapor, right? So if there was a greenhouse, and then we got very close to the right, like basically spot on, got the exact answer, right? Um, this greenhouse effect they talk about should be doing some other temperature shit stuff to the atmosphere, right? And so we should still be way off, but we're not way off. We're dead on. So what does that mean? It means that it's not really a greenhouse effect, is that right? We're going to get into that later. So the temperature structure entirely explained by ideal gas law. No other effects? No, not really any other effects. Nothing that we've really talked about. So yeah, if you I would want you to study this diagram and recreate it from scratch on a blank piece of paper in the exam, just to indicate that you comprehend how the Earth is heated, how you get its effective temperature, and the basic properties of the atmosphere being explained by the adiabatic gradient and the water vapor latent heat release. Okay, cool. Generalization. Thought experiment. What happens? What happens if you remove a shell of Earth's crust and replace that with atmosphere of the appropriate pressure and other variables as a function of depth? Assuming that Earth's mass stays the same or negligibly changes. So 8 minus 18C would stay at the same location. At that altitude, there's no diurnal changes with temperature. It's pretty constant there at 5 kilometers. So minus 18C would stay at the same location because we're not changing anything up in the atmosphere. We're just replacing a shell of the ground surface, say a few more kilometers deep, with the amount of atmosphere that you would need for everything above it just to stay the same, right? You're just continuing what exists at the normal gradient and pressure and temperature and volume down to the surface, getting rid of some surface and just replacing it with the atmosphere that would need to be there, right, for it to just continue on. So what would happen? Well, the bottom of the atmosphere would get hotter and hotter the more depth you do this experiment, this thought experiment with, because of the lapse rate, right? Minus 18C is staying up there, but now you're going deeper and deeper and deeper, applying this lapse rate, it's going to get hotter and hotter and hotter. I want to ask you, does that remind you of anything? You heard of any other planets, maybe? You could apply that to? You guys, what do you think? So there's a question for the class. You think you'd maybe apply that thought experiment to any other planet that might be useful? Another planet that has a rocky bottom? What planet could you maybe apply that to? Excellent. Perfect. Venus, exactly. You apply that to Venus. You apply what I just did, what we all just did in class. You apply that to Venus. Well, Venus's atmosphere is 90 times Earth's atmospheric mass. 90 times. You have any idea how much more, well, it's 90 times. It's a lot, right? 90 times Earth's atmospheric mass and 90 times its depth. And if you work it out, you nail Venus's ground surface temperature, which is like, I don't know, whatever it was, 700 Celsius. It's way up there, right? Perfectly. So, this yay, physics is universal. Very cool, right? So it's a general. What we derived works generally, where you have ideal gas law applying to gases and other atmospheres and planets. I mean, with a rocky bottom with ground surface at the bottom. Neat, right? So it shows that we're doing some really basic fundamental physics that, physics is universal, applies everywhere, right? Pretty cool. So this would just be a few more comments. Feedback and stability effect of water vapor is to significantly lessen the adiabatic gradient. So that makes it cooler at the surface than the dry rate. If the dry rate only existed everywhere, the Earth's average temperature at the bottom would actually be plus 22C. And actually, I have some old books which actually list plus 22C as the Earth's average surface temperature, because they used to just think about it in terms of the dry lapse rate, but now we incorporate the wet lapse rate, and that's what brings it down to plus 15C. So it's actually a little bit cooler. They call water vapor the strongest greenhouse gas, but its effect is actually to make the surface cooler than if it wasn't there, than if it didn't exist, right? So does their greenhouse effect theory make sense when it predicts the opposite, right? Because under their theory, having a greenhouse gas, the strongest one, that's got to make the surface hotter then, right? But its presence actually makes the surface cooler, right? Tropical areas versus desert areas at the same latitude, meaning they get the same solar heat, are always cooler. So that means the humid areas, obviously, tropical areas which are humid, always cooler, maximum daytime temperatures, and actually on average too, their average daily temperature is cooler as well. Warm air holds a higher amount of water vapor, and therefore there's negative feedback to warming because the warmer the air gets, the more water vapor it holds, but then the more resistant because of the latent heat phase it is to warming. So big negative feedback to warming due to water vapor presence. On the other hand, the effect of latent heat is also to slow cooling and the freezing of air. So there's also a negative feedback to cooling because you water your garden before a frosty night because that water there is going to keep it from freezing. Um, Humid nights cool down less because of the latent heat from water vapor. So there's on both ends, the heating end and the cooling end, you have negative feedback, huge negative feedback from water vapor, right? Stops it from warming as much and stops it from cooling as much. So water vapor and a semi-thick atmosphere makes Earth's surface climate very nice and stable. Compare that to the moon, which is airless and waterless, and that goes from plus 121 degrees Celsius in the daytime to minus 150 degrees Celsius at night. So summary. So this is the summary. So and the summary is how to get Earth's temperature. One, get Earth's effective temperature. So just understand that this is not the ground surface temperature and shouldn't be thought of as such. Atmosphere is an integral part of the Earth ensemble. Perhaps later we can liken this to an expected average temperature of the system, as of course we do, right? Derive the lapse rate would be the next thing, and then factor in your latent heat release from water vapor. Existence of lapse rate necessitates that any expected average cannot occur at an extremity, as per the definition of what an average is. Integrate lapse rate to get the temperature as a function of height. Use the effective temperature as an expected average, even though Earth isn't a black body, but what else can we do, right? These are the values we calculate from first principles, and then we have our empirical, noisy measurements. But what else can we do? It's literally all we can do. So use H naught where the effective temperature physically occurs in the atmosphere. That occurs where it has to due to the ideal gas law. Calculate temperature at H equals 0, very close result to the empirical surface temperature measured 0.3% error. Man, that's way within our error, theoretical error, given all the assumptions we're making with the averages and local thermodynamic equilibrium and stuff. That's fantastic. Um, Surface higher temperature is going to be slightly higher for the reasons we discussed. And what's awesome, finally, is that the temperature profile of the Earth is entirely explained with no radiative greenhouse effect. That's how you do it. Boom. Nice, guys, right? So here's a couple summary sort of slides. So you already saw this energy budget. This is how it would kind of look. This is how you would draw it for a column of atmosphere on the right here. So you have your near surface average. You have your average where the effective temperature is found, around 5 to 6 kilometers. And then you have your top of troposphere, which is around 18 kilometers. And then this is just to show that you have adiabatic compression, adiabatic expansion. That's what leads to this equation. This equation just being the dry rate. And that's just minus G over Cp, the dry rate, or the wet rate. You would just insert what that value is supposed to be, minus 6.5, right? So basically a couple of schematics here, and we've explained the temperature of the Earth entirely, all its major features. And we also have a value of sunlight here, which can create the climate, which is pretty useful, right? Very nice. So maybe I'll just take a break. I do have quite a few slides left actually, but that would be the lecture proper. We would end with that. We're going to continue now and make comparison to the greenhouse effect method of doing this, right? So Yeah, I'll just go over to this chat and see if you guys want to say anything for a few minutes. I need some water badly. Yeah, good. Venus. Everyone got that? Yeah, that's right, Louis. Excellent. Just go ahead. All right. I'll just go ahead then. Let me just have another drink then. Well, the ZM, the depth of the troposphere would be rising, right? Because we're just, what exists here would just remain, and then we're just replacing what would be below with just what would need to be there for atmosphere. So we're going to remove a shell of the Earth's surface and just replace it with the atmosphere that would need to be there if you just continued that distribution that exists down, right? Yeah, that's the science now for the politics. Yeah, exactly, Phil. Yeah, exactly. So, yeah, this would be good, right? You guys can show this now to anyone and be like, look, it's done, guys. It's done. We can totally solve the temperature of the surface of the Earth um, entirely from first principles, basic physics principles, and without what you guys are going to see as this ridiculous, a lot of you obviously already know, this ridiculous greenhouse effect idea. Yeah, Malda B is making a good point there about Venus temperature at 1,000 millibars, 15C adjusted for 1.91 times. Yeah, yeah, right, exactly. Okay, I'll continue on then. Perfect. Right, so point of departure. Where does the prevailing narrative depart from the development shown here? Let's check. Let's go back to slide 10. You know, I don't know what slide 10 is anymore. I won't be able to find it. I just have it here. What's the point of departure? Um, Where does the prevailing narrative depart from the development shown here? Let's check. It's actually in slide 10. It's at the part where I asked you, should minus 18C be everywhere? The standard prevailing narrative says yes. You guys all nailed it. You're like, no, why the hell would the temperature be the same everywhere? Why would you say that? They do say that actually. They say minus 18 degrees should be everywhere. It treats, this is another thing that they do, they treat the effective temperature of the Earth. Oh, I should have had T effective Earth there. So that means, yeah, so here I'm referring to the effective temperature of the Earth as the solar input. And if you do that, the sun cannot create the climate or the weather, which we'll get into in just a second. It treats Earth as a flat plane. Sounds a little bit silly, but ultimately that's what their problems all stem from and where their greenhouse effect idea comes from, is from doing it that way. They actually don't ever mention in their standard greenhouse derivation, they completely leave out the lapse rate derivation and the wet lapse rate derivation. They never discuss it. They put it all in terms of a greenhouse effect instead, right? Look at what we did. We incorporated this lapse rate, the adiabatic rate, how you can calculate it from first principles, and incorporated that because it's an integral part. It's a fundamental integral part of how the atmosphere works. It's like the core part of what the atmosphere is doing in a gravitational field. Like how the hell could you leave that out? It's so freaking important. It's like the thing to know about the atmosphere, and then especially, right, adding in that water vapor component, because if you don't add that, you're way freaking off, right? You're almost 50% off, right? That's like such an important thing to show. They leave that out. It's completely out, right? And then, yeah, it assumes that the effective temperature of the Earth, minus 18C, should occur at the bottom of the atmosphere, the hottest, which has to be the hottest part of the average due to the lapse rate, instead of at the average. So, of course, if you leave out the lapse rate, then you don't have the idea that there has to be a distribution in temperature. By definition, if there's a distribution in temperature, the average has to occur around the middle, and the middle is not at the surface, right? But since they leave out the lapse rate, they forget all that and then just say, oh, minus 18C should have occurred at the surface, but it never should have in the first place, right? So let's look at this. Here's a diagram showing a bunch of different universities that have done it, that do it. They probably, yeah, I think they still do it. Um, They've actually, a lot of them have taken down these plots, but luckily I saved them. So look at this quote from Roy Spencer. He's a famous climate scientist. And he says, sunlight does get spread over the full sphere of the Earth. And he was saying this to me, how can you dispute that, Joe? It's the starting point for all of climate science. So what are they doing in all of these diagrams at all these different universities as a standard derivation? What do I have ahead here? Yeah, I'm going to compare it up here. So just this is just to make the point and appreciate that this is the standard development. This is the standard derivation. This is what they do. So here's Harvard's version. Here's the University of Chicago, a guy up at a professor. I think his name was David Archer. Teaching it. And look at, he's got the exact same thing. He's calling it the greenhouse effect. He's got the same sort of lines and arrows as here. Columbia, Pennsylvania State, so all over the place. And here they do have a little bit of a curve right here. But the important thing is to look at the math, because the math tells you what they're actually doing. So the math here, the numbers they're using, still come from these exact same diagrams. Even though they put a little curve here, they're still using. And so what do I say? Well, yeah, using this a plane here, right? So what do I say here down at the bottom? What do I ask? These diagrams demonstrate the universal starting point, as Roy Spencer, world famous climate scientist, admits, by which climate science then derives its greenhouse effect and does all the rest of its science. Look past the math and see what the math is being developed for. What is a flat line representing the entire Earth called? What do you call that? What do you call that? That's right. You call it flat Earth theory. I mean, if you were to talk to a flat Earth theorist, like one of these trolls on whatever site you can find, I mean, Gab is a flat Earth group, and you ask them to show you a side view of the Earth, right? What would they show you? They would show you these diagrams. Isn't that freaking great? Isn't that great? Is that so funny? That's so freaking funny, man. Okay, so which one, right? So compare mine, and we're going to get into more details about all this as we go on, okay? Versus theirs, right? So with my model, this isn't even mine. I don't like to say my model because this is not, it's not mine. I'm just showing you what is. This isn't mine, right? I'm just showing you what is empirically, right? Like just because I wrote this down doesn't mean this is Postman's model. It's just freaking what exists, right? Sphere Earth, hot sun, it's coming in, the sunshine is really hot, and what do you get from that? Just from a basic intuitive, or not even intuitive, just a basic comprehension of how the energy comes in, how the heat comes in, and how it goes out, right? Well, the sun creates a climate. Why would the sun create the climate? Because it's hot enough to at the Earth, right? You go outside and feel the sun in summer. It's quite hot, right? It's actually above the atmosphere. It's damn hot, 121 degrees Celsius, right? Scorching, right? You would immediately identify that the climate is the transfer of solar heat. That's what climate is. It's solar heat coming in, transferring through all the gas and water and making the climate. That's what it is. The input transfers through to the output. It's physically and mathematically realistic. It's consistent with thermodynamic laws. It's empirically observable. This is what you would literally observe. I mean, obviously not the lines and crap, but I mean, in abstract terms, you would see a Earth that's half lit and the other half, which is in darkness, and this is what you would empirically observe. Interestingly enough, this is not acceptable to peer review science, and we're going to get into some of their comments that they made about this. It'll blow your mind. On the other hand, this is the standard procedure. Sun cannot create climate. Now look at this term here. You see this. So Fs, that's F sun. So this is incoming solar radiation. Look very closely. Fs times 1 minus A over 4. Where have we seen that before? It's right here on this page. Where have we seen that before? Oh, that's the effective temperature of the Earth. That's this right here. Oh, and what's that value? Minus 18 degrees Celsius. Oh, wait a minute. They're using the effective temperature of the Earth of minus 18 degrees Celsius, and they're calling that what? Incoming solar radiation. Well, why do I call the incoming solar radiation 1,370 watts per meter squared and plus 121 degrees Celsius? That's weird, right? What a strange discrepancy. They're calling the incoming solar radiation the effective temperature of the Earth instead, right? Look, see, F sun 1 times 1 minus A over 4. That's weird. Why are they doing that? And then they got a whole bunch of other stuff going on. So what happens when you do that? It's because they're doing flat Earth. And the way this works out in the math is it forces you to use the effective temperature of the Earth as the solar input instead of the solar input as it actually is. We're going to get in a couple slides as to why math gets screwed up when you don't use the correct empirical thing that actually exists. Really fascinating, really great philosophy of science stuff. It should be in every single physics and philosophy of science classroom out there to teach what happens when you don't get your models right, right? It would be really good. So it's literally a direct consequence. It's a direct consequence of using a flat Earth that you then have to use the temperature of the Earth as the incoming solar radiation instead of just using what is the incoming solar radiation. Isn't that neat? So what happens is that if you think that your incoming solar radiation is only minus 18 degrees Celsius, well, what does that leave you wondering, right? What does it leave you thinking? It leaves you thinking, how the hell can the planet be warmer than minus 18 Celsius if the sun is only minus 18 Celsius worth of heating, right? And and of course, why are you thinking that? You're thinking that because of your flat Earth paradigm, and then you come up with some other physics to explain why it's warmer than that, and that's what they call their greenhouse effect. But they're just creating a fiction because we're in the realm of fiction in the first place. So we created some fictional scenario of flat Earth and cold sunshine. So what do you do to make it better? To make the ground warmer? Well, you create more fiction to fix that fiction, right? But it's still all fiction, right? So the end result of their standard procedure is that the sun does not create the climate and cannot create the climate. You get the climate creating itself out of nothing. You reverse the Earth's output and you use it as the input. It's mathematically, physically, theoretically, and graphically literally equivalent to flat Earth theory, to flat Earth. It's inconsistent with thermodynamic law. I don't think I get too much into that into these slides, but basically it requires the cold atmosphere to send heat back to the warmer surface, which means that would have to flow from cold to hot. I mean, that is part of it. They always try to deny that and get around it, but they're just defending their fiction at this point. They refuse. It's like when I show this to them, it's like they don't even see. It's like there's some filter in their brain and they can't see this left side here, and they just can't. They're like, no, no, I've had some of them be like that before when I'm debating them a long time ago. It's on my YouTube, and they're like, I didn't come here to see an ulterior model. No, I'm not going to see your model. No, I don't want to look. I just want to talk about why there's a greenhouse effect and why you're wrong in criticizing it. And I'm like, oh well, I have a whole other model to show you how it would work without it. They're like, nope, nope, not going to look at it. They literally can't look at it. They just can't. It would like burn their freaking eyes out or blow up their brains or something, right? Um, yeah, so inconsistent with thermodynamic law with the reverse heat flow. Heat cannot flow from cold to hot. Heat only flows from hot things to cold things, right? It's empirically fictional, right? It is a fiction. It's a fake version of a greenhouse effect. Yeah, that's right. So what they're indicating here with these arrows, this should actually be how, or in theory, it could be how a real greenhouse works. You could apply this scheme, this thinking to a real greenhouse where this would be the roof of the greenhouse and this would be the bottom floor of the greenhouse. And you should get this scheme working. If this thing works, like they say for the atmosphere, it should work for a real greenhouse. If it works for a greenhouse, it should give some empirical result indicating this mechanism is in play, but no real greenhouse shows with the results of the temperatures you get inside a greenhouse. None of them show that this mechanism is in play, which means it doesn't exist, right? Because you just get the temperature inside a greenhouse as you get from over here, from the temperature of the sunlight, solar heating into the greenhouse. And it ends up though that this is peer-reviewed climate science. So I'd written a paper. Oh, I should link that. So actually, I put this slideshow into the description, both on my blog and on the YouTube link. I should actually include the paper where this table comes from. It's the paper that was in my third book, Planet Wars. I should let you guys just have that paper because it's still a great paper. Um, so basically just some differences. Global energy budget, so standard model versus thermodynamic model. I mean, is basically what I have here, but I'm just saying it a bit more scientifically, right? So solar input geometry, standard model is evenly over the entire spherical surface represented as a flat plane. So they got no day and night, no Earth rotation, anything, right? What's actually happening, like I said, it's not my model, it's what actually exists. Solar input is actually only over a single hemisphere ever at a time, daytime, as a function of zenith angle, just meaning that sun is strongest right, right at the equator at noon, and the strength of the sun obviously drops off towards the night side, right? Heat flow, they need it to be reversible and recyclable, whereas this in reality, heat flow should only be and can only be unidirectional from hot to cold. The climate in the standard model is a secondary consequence of heat recycling, which they call the greenhouse effect, which, as we said, can't be measured and violates the laws of thermodynamics. Whereas in reality, the climate is a direct consequence of solar heat flow. Solar flux in their model, it's insufficient to create a climate without heat recycling because they're using minus 18 degrees Celsius as the solar input when actually that's the Earth's effective temperature output. Um, Whereas if you just do it as it actually exists, you have plus 120 C input. Well, that's probably sufficient to create the climate. 121 degrees Celsius, that's definitely enough to melt ice, definitely enough to evaporate water. So it probably definitely is the sun is the sufficient force to create our climate, right? Um, Empirically, there's this fictional, and empirically, this diagram here on the left, that's observable. That's what you would observe. Thermodynamically, they're inconsistent with theory, and in reality, you should be and strive to be consistent with theory. Great. So, yeah, the one point, valid versus invalid fiction. So, working out physics. Now, this is such a great philosophy of physics concept, which, should be in a philosophy of science, philosophy of logic course. Working out physics for fictional things leads to impossible results. That's such a great comment. I came up with that myself. um, because they're working out the physics for this flat Earth. And what does it lead to? It leads to impossible results of reverse heat flow, heat having to flow from cold to hot, and the solar input having to be freezing cold at minus 18 C instead of what it actually is, right? So working out physics for fictional things leads to impossible results, right? Now, here's a great question. Oh yeah, I want to ask you guys this. Orbital mechanics for flat Earth. Why not? Why can you not do orbital mechanics for a flat Earth? You could actually apply the equations of orbital mechanics for putting rockets into space or cannonballs. You can apply that to a flat Earth and work out the value. Do you know what the speed is to orbit? So in the chat classroom, what is the speed that a cannonball would have to be in order to orbit a flat Earth? What would the speed of the cannonball have to be to orbit it? If you had an infinite plane flat Earth, what would be the speed that a cannonball would have to be in order to orbit that? Yeah, I love all these comments up in here, you guys. Oh, that's so good. Yeah, Louis, exactly. Yeah, shakes your confidence and also, yeah, absolutely. Read my Planet Words book, man. Honestly, read it. You will be shocked. I mean, well, that's a pretty, I mean, yeah, that's really plunging you in there. I got other books. Maybe you should read actually The Layman's Guide to the Greatest Scientific Fraud in History. Read that one of mine. The Layman's Guide to the Greatest Scientific Fraud in History. Start there. Nice answers, guys. Nice. I like that. Yeah, so it'd actually be infinite velocity, right? You're right. It would be infinite velocity, and Carly's right too. It would be impossible. And Boomy's, going to light speed because obviously Boomy knows that the speed of light is the ultimate speed you could get to, which means infinite speed. But yeah, if you worked it out, the math, it would actually come out to the number infinity, which, as Carly says, uh, is impossible, right? So working out physics for fictional things leads to impossible results. It's impossible to have an infinite speed, isn't it? Um, so you can work it out, but it doesn't work out right. Thermodynamics for flat Earth. So in analogy, right, as we've been discussing, thermodynamics for flat Earth, what happens? Impossible heat flow. Now here's the thing. Not all approximations or fictional representatives are valid. Now, some are, right? Now, think of the fiction of a free body diagram. I don't have a slide for this drawing it, but maybe you guys know what I mean by a free body diagram. Like a free body diagram with Newton's laws, where you just have a little square, right? So we just have a little square, and that square represents the rocket, and then we use little arrows, and we say there's friction, and there's thrust, and other things happening to this square representing the rocket, and then we calculate And this square box has a mass, and then we calculate how that thing accelerates, right? So the fiction of a free body diagram just being a square box that represents a rocket, that is a valid fiction for depicting total force and doing calculations and putting a rocket into space. But the friction of a flat Earth is not a valid fiction for depicting the solar input. So it seems a bit confusing, right? Why would the fiction of using a square box for a rocket and a square body and a free body diagram with Newton's laws, why would that work? But why does the fiction of using the Earth as a flat plane not work? They're both kind of just fictional representatives, right? The square box being a fictional representative of a rocket, flat line being a fictional representative of the Earth, right? This is such great philosophy of science stuff. This will hopefully one day be, discussed in science courses and philosophy courses because it's pretty important stuff. So what's the difference? This is important. The difference is if the fiction dictates and determines the mathematical topology, what I'm just going to call the mathematical topology, right? So when you use a square box as the rocket, you're not saying that the friction that that rocket experiences is the friction that the square box would experience, right? You're not treating the math as applying to a square box flying through the air. You understand that it's just a square box, but it represents a rocket, and that rocket has its own aerodynamic properties, which you would have to factor in, right? Whereas when they do this flat Earth thing, that flat Earth is determining what math they have to use. So the flat Earth is determining what math they have to use, and that's what leads to the impossible result. So when you use a little square box for a rocket and put all that forces, that square box is not determining all of those forces and all those elements. We understand that it's not a square box flying through the air. It's a rocket that has its own aerodynamic properties and et cetera, et cetera, et cetera. The square box does not determine the math, and that's why it's a valid fiction. So the reason why the flat Earth fiction is invalid is because that flat Earth is literally being used. It's being used literally as what the Earth is, and they're applying the math to that literally, right? See the difference? It's an important difference, okay? And it's really cool to think about philosophically. So consequences of incorrect science. What are the consequences of doing this wrong? You know, what I just showed you with the lecture. What are the consequences of doing this wrong? In contrast of this presentation to the prevailing narrative, here's a good point, demonstrates the philosophical idea that false science leads to false knowledge, and that false knowledge equates variously, going back, to the ancient Greeks and all the great philosophers. What does false knowledge equate to? Death, anti-God, anti-Christ, if you want to call it that. It's destruction, and of course, contradiction, right? And so we're going to get into this in more detail, but just a couple points, right? What do they want to do? So they have this greenhouse effect, which is based on fiction, based on flat Earth, and it's made them be afraid of the weather, and it's made them think that there's a greenhouse effect that's going to, cause planet boiling, they're calling it now, global boiling, but it's really just normal weather that's always existed, right? So what are they doing? There was just an article a couple weeks ago where Bill Gates is cutting down vast tracts of forest, right, in order to capture the CO2 from those trees and then bury them underground, right? They're removing CO2 by various means. We're going to get into the means they're doing it, but they're removing carbon dioxide. It's a pretty big deal because carbon dioxide is actually the basis of life in photosynthesis. The atmosphere right now actually has a little bit too little. It could use a whole lot more actually. In real greenhouses, we pump them with 5 times the amount of carbon dioxide because the plants just love it. They grow way better. That's how they evolved. We're actually in a CO2 dearth right now. There's actually not enough. It's very, very low. And then we're going to get into how they want to block sunlight. They actually literally want to block sunlight, and they say that's good for the environment. They say, sunlight being the basis of, along with CO2 being the base of photosynthesis, being the basis of basically all life on Earth, and they're saying they want to get rid of these things that are the basis of life, carbon dioxide and sunlight. They want to block out the sun. They want to engineer bacteria to remove carbon dioxide. Imagine if that bacteria, once engineered, got loose. Of course it's going to get loose. Of course it's going to escape. It's whatever lab they're creating this in. And What if it just gets free, loose into the environment and eat and consumes all the CO2? I mean, they seem to have forgotten, or they know, and they're doing it on purpose, that if you get rid, and you don't have to get CO2 down to zero, you just have to get it to actually not much lower than it was pre-industrially 100 years ago. You just have to go, I think it's only another 25% lower, and photosynthesis stops. And when it stops, what does that mean? The end of photosynthesis. That's like base of the food chain. That's everything. That's worse than the frickin' dinosaurs, right? Like total extinction level event, total extinction level event, right? So it's a pretty big deal if you get it wrong, but they really seem to really badly want to get it wrong. We'll get into that. Um, oh yeah, so I got a bunch of stuff here. So this text might be a bit small for you to read. I just want to get all on one side, but I'll read it. So what follows here is the conclusions from a fictional flat earth theory and its resulting impossible physics and all the things that they want to do as a consequence of that. So here is an example from this site. Solar radiation management offers the possibility of cooling a planet significantly on a time scale of a few years. God, guys, cooling the planet significantly. So solar radiation management means they want to blot out the sun, right? Because that's good for the environment. And look at what they say here. Politicization around climate change has obviously been a huge driver of policy gridlock, or the poor babies, on reducing carbon emissions. And so I think we should try to avoid politicization around engineering. She means solar radiation management. So what they're saying is that they don't want to have to go through politics and through government. They just want to go ahead and do it. They just want to go ahead and block out the sun and not have to go through government. It's a bit worrisome, yeah? Policymakers in the EU have signaled willingness to begin international discussion. So, I mean, they're freaking moving on this internationally. They're moving on this, guys. Um, Discussions of whether and how humanity could limit heating from the sun. It's interesting that they say they want to limit heating from the sun when the basic basis of climate theory now is to say that the sun doesn't really heat the earth above. So it's an interesting sort of self-contradiction, right? But interesting that they want to limit heating from the sun, right? Guys, what do you think of that heat? Yeah, I mean, I hope you see this how I see it, right? You don't want to limit heating from the sun. You don't want to limit sunlight. That's the basis of life, right? So climate change is already having profound effects on the physical and natural, well, they just make up, that's just bullshit, on human well-being. And these effects will only grow as greenhouse gas concentrations increase and warming continues. Understanding these impacts is crucial to enable informed decisions around a possible role for blocking out the sun, solar radiation management, and addressing human hardships associated with climate change. So funny, right? Understanding these impacts is crucial to enable informed decisions, right? And like what I set up here, informed decisions within what the context of what paradigm? The paradigm of a fictional flat earth theory and the resulting impossible physics which have come from it, which they call the greenhouse effect, which is, this impossible physics where carbon dioxide is what basically creates the climate, right? Yeah, so I think maybe you're not quite informed there, are you? EU leaders open the door to international discussion of blocking out the sun. 60 leading scientists. Oh, well, hell, they have 60 leading scientists. Of course, they're leading scientists who say that you should block out the sun, right? Well, you better go ahead if the 60 leading scientists are telling you you should block out the sun, well, because of flat earth theory and impossible physics, you probably should. Signals the U.S. government to be supportive of well-governed research, including outdoor experimentation, which means just going ahead and doing it. All right, so from the Times of Israel, oh yeah, so this is the one where they're engineering CO2 or engineering bacteria to eat CO2. Possible climate breakthrough. Just gonna make sure my mic is still working. Yeah, perfect. Israeli scientists engineer bacteria to eat CO2. Decades-long research at this institute could pave way to remove excess global warming CO2. Like, what a stupid frickin' name for CO2. Excess global warming CO2 from the air. Yeah, CO2 is only the basis of all life. And, we were very close to frickin' having a total extinction level of event before it started coming back up just 100 years ago. Like, my God. In a remarkable breakthrough, researchers at this stupid institute have produced a genetically engineered bacteria that can live on carbon dioxide rather than sugar. So imagine what happens when that gets loose out of the petri dish. What happens? What happened supposedly with COVID and the storyline that it's um, this accidental release from a petri dish, right? What happens? Except now put it in the context of carbon dioxide, and it's a bacteria that's eating all the carbon dioxide freely. It got loose, and now it's just covering everything, coating everything, growing exponentially. It'll exponentially replicate until it sucks all of the carbon dioxide out of the atmosphere. That's what will happen. And what happens then? That is the end of all life on Earth. Like, you thought them dicking around with their gain of function research and doing this COVID thing was bad? Like, this is infinitely worse. Um, John Kerry on carbon dioxide. Even if we get to net zero, we still have to get carbon dioxide out of the atmosphere. He's not even saying how much. He's not saying, we need to reduce to. He's just saying we need to get it out, all out. Like, they'll get it all out. That's what they're going for. Bloomberg Business. What if we blotted out the sun to fight global warming? Cutting off sunlight to fight climate change could be necessary. Here's Forbes, similar idea from a different source. The idea is to build something that would stay between us and the sun all year long. So in this article, it was discussing putting a giant solar sail at a Lagrange point. That just means a point that's stable gravity. You can put something there and it'll stay there between the Earth and the sun basically forever. Because it's a gravity balance between the Earth and the sun. So they want to put a giant solar sail there, a giant one, like a big, massive one. It would be like, huge, hundreds of thousands, whatever kilometers across, some big freaking thing. Build it out of some sort of self-replicating nanobots that use like an asteroid or something that they place there, and it would just build itself. Could you imagine doing that? Yeah. Yep, that's what we should do. We should put a giant umbrella in front of the sun, right? And look what they says. Oh yeah, oh yes, I love this one. This is one of the most ambitious, but also one of the sanest options we could possibly consider when it comes to combating global climate change. Sanest, yes. It's very sane, isn't it? Because 60 leading scientists say we should do it. We should put a giant umbrella at a Lagrange point where once it's there, you can't freaking get to it because it's a million kilometers away. What are you going to do? Nuke it to get rid of it? No, obviously they wouldn't allow that. So yeah, this is a very sane thing to do, right? Now, of course, if you're not aware, in my Planet Wars book, I have the paper that I, tried to summarize all this and put it through peer review so that they could, maybe we don't have to go ahead with this, right? Um, so the peer review of my proposal that we use a spherical Earth where the sun creates the climate, and I get these, what I just call impossible responses. These are responses which are simply not possible in a normal world from normal scientists, right? So this was the first response from the Bulletin of the American Meteorological Society. This is in peer review, their peer review response. I have all this fully documented in my Planet Wars book, by the way, if you want to go see if you haven't yet. Look what they say. The proposed spherical model is incomplete and quite wrong in so many ways. And then regarding my comment that the sun creates the climate, his response was, this is nonsense. So think of that, what he's saying that about, right? Remember just a few slides back at the comparison between my round Earth, not mine, what actually exists in the round Earth with hot sunshine versus their method of using the flat Earth. And he says that my proposed spherical model is incomplete and wrong in so many ways. Let's go back. Yes, this is incomplete and wrong in so many ways, right? That the sun is the value that it actually is, hot, that the earth is actually round, that there's an actual day side and night side, that the output is, it's just my daughter there bringing the, and wife putting puppy to sleep. Um, minus 18 degrees Celsius is the actual output of the earth. That's just wrong in so many ways. Oh, but this is right. This is completely and entirely right and entirely acceptable, right? I mean, think of just how insane that is, right? Okay, go ahead. Next one. This is from a different paper. There should be some solid theoretical evidence provided to support that your proposed idea was a better model, which would lead to some scientifically significant results. Well, that's what the whole paper was about. The significant scientific result is that the sunshine is hot, that the sunshine can create the climate, and the way you're all doing it right now is to say that the sunshine can't create the climate and sunshine is freezing cold because you're using a flat earth. It's kind of a difference. That was why I had that table, right? What I have in the table. The sun creates a climate versus the sun doesn't create the climate. Don't you think that's, I don't know, neat? Isn't that kind of scientifically neat? No. No, there's no evidence. No evidence. Basically, they're saying that there's no evidence that the Earth is round, is what they're. That's basically what they're saying, right? No compelling evidence or analysis for a new approach model. Much more extensive underpinnings are required for new scientific claims. Yeah, to the commentator who said you've lost all your faith. Yeah, yep, in science. Much more extensive underpinnings are required for new scientific claims. So this round Earth, right, is a new scientific claim, and I need to come up with a whole bunch of frickin' extensive underpinnings for that suggestion. Oh, but that's fine with the flat Earth and cold sunshine. That's fine. This is impossible, right? Right? I, if you haven't read Planet Wars, I get all into totally analyzing their psychology and what has made them this way, right? Because these are impossible things. There's going to be a few more. Think of me as a science, I came from the country from a very hard life. I was frickin' smoking when I was smoking cigarettes when I was 7. I was drinking heavily when I was 12. Like I had a very, very fun but hard country life. And somehow I got interested in astronomy when I was 17. Having failed, I had failed. I was in grade 11, supposed to be in grade 11, but I was still taking grade 9 just because I did not go to school and I did not give a crap. You know, I was drinking and smoking and stealing porno mags from the corner store. Um, um, I just did not give a crap. Somehow I got interested in astronomy, and I just started taking courses on the side, math courses, because like, oh, it looks like I need to know some math to do some astronomy. And eventually I took a grade. We had streaming back then, advanced general level, and I took a general level physics course. And and the teacher, this is like a grade 11 course, and the teacher said to me, the high school teacher, he was like, Joe, you're really interested in this. You could go to university for this if you really wanted. Do you know what my response to him was when he said I could go to university to study physics? I said to him, what is a university? Isn't that funny? Eventually, I did it, and my career was great, and I got working with the Canadian Space Agency through the University of Calgary, doing space telescope stuff, studying stuff in space. But think of me coming from the country, just an innocent, stupid country bumpkin ground um, uh, country boy, right? And now I'm in a place where scientists are saying the strangest frickin' things to me. This makes no sense, right? It really makes no sense. Well, I applied everything that I've learned in life. You got to read Planet Wars. You should see what I do to these people. Like it's just so bad. They're trash so bad. And then I actually explain and figure out what they are. And you'll be really surprised at that. Okay, so another journal. Um, that was it was a pedagogy journal meaning how to teach physics, teaching ideas. And their response was, our journal deals with subjects that would be adequate for university level teaching. Well, that's exactly what this is. That's where that flat Earth diagram, it's taught in second year physics. My, round Earth diagram could be taught easily in second year physics too, like like the name of this lecture, right? Not with scientific quarrels or alternate interpretations. One might conceive, yeah, it's just some weird random conception, right, that I come up with, treating the Earth as round and seeing how it works with the math that way, right? And then they said, I believe that your approach should first be vetted by experts who could validate and invalidate it. And I'm like, that's what you're supposed to be. That's why I sent my paper to you as a peer review journal, right? You're supposed to be the expert to vet it. And they're like, no, no, no. We need other scientists out there. You need your 60 experts, right, to tell us it's okay to publish a paper saying that the Earth is round and that it makes a difference for the climate, right? These are impossible things. Like, this is an impossible world for me to live in. But what's that quote? I just heard that quote today. What was it? Once is coincidence, twice is incompetence. Is that right? And then 3 times is purpose. And basically that's what I did. I think it's a quote, something like that. Anyway, that's what I did. I found out, I basically determined that it's purpose. They're being purposeful and they're being sneaky little liars and they're doing it on purpose. Yeah, so the arguments made for consideration of an alternative energy budget model are ad hoc, right? So this journal says, these are all major journals, by the way, and I name them in my book. There's all major physics journals, are ad hoc. That means just made up, right? In Latin, it just means just made up. So my depiction of the Earth being round with a sunlight as it actually occurs strong enough to create the climate, that's just ad hoc. It's just made up without justification or mathematical rigor. Oh, but their flat Earth and the math they have there, that's totally mathematically rigorous, right? That's totally mathematically rigorous, and it's totally justifiable. But this round Earth thing you're doing, man, you're just making that up. What's your justification? You have no math to show that. I hope you guys are laughing along with me, right? And then variously one-on-one with me talking to some of these people. So you get these stupid things. Heat flow from hot to cold only does not apply to radiation. So they like to say that there's an exception to the laws of thermodynamics to radiation, which is simply bullshit. It's not true. Heat only flows from hot to cold with radiation as well. Radiation, anyway, it's just one of the modes of heat flow. It's just a freaking lie, right? This was one we got recently. I think I talked about this. Who is this with? Oh yeah, this was with that Mike Merrifield guy. You don't understand a cartoon with planar geometry? Oh, you idiot, right? It's like, no. Uh, I do get that it's a cartoon. That's fine. And yes, I am pointing out the planar geometry and comparing it to why not treat the Earth as round? I mean, just why not, right? Like, why not? Why not give it a hello, hello? Okay, it's going. Yeah, these things seem to have an auto off too. Says my mic is fluttering again. Um, I can't wait to come back and read your guys' comments after this slide. Yeah, so planar geometry. You don't understand a cartoon of planar geometry? God, right? It's like what do you call that? Gaslighting. This is gaslighting, right? Uh, this was recent. I got this. I'll just call this. I got this comment from a guy named Rick from my old work from my university. Cannot communicate my level of disrespect for you. You have a dangerously ill-informed model. Can you guys frickin' understand the world I live in? Like, this is a professor of physics, right? And he says to me, after showing this model, this doing it with a round versus flat, he says, I cannot communicate to you my level of disrespect for you. It's dangerously ill, you are dangerously ill-informed with what you're saying. How the heck does it make sense, right? Read my Planet Wars. Um, Red herring, misleading instruction, not worthy of attention. Oh yeah, he says your comment isn't worthy of attention. The GCMs use a spherical Earth. Well, yeah, so that's I mean that's one thing you get. Oh, that's not worthy of attention. The global climate models use a spherical Earth, and sure they do, but that's a red herring. It's not about the global climate models. It's about the idea of a greenhouse effect and where the greenhouse effect comes from. And the greenhouse effect comes from this fictional flat Earth and its resulting impossible physics, which means that the greenhouse effect doesn't exist. Which means if they're putting it into the global circulation models, global climate models, they're freaking wrecking them, right? It shouldn't be there because it doesn't exist, right? So it's just a red herring, right? And they love that, right? Okay, so after all this, and as I conclude in my Planet Wars book, they really do want to end all life on Earth because these comments are impossible. These comments indicate purpose, right? So they really do want to go ahead with all this shit here and block out the sun and remove carbon dioxide, which results in what? Ending life on Earth. They really do mean it. They freaking mean it. How can you not take it? I mean, you have to use the de facto clause in law, right? If you act like you're trying to destroy all life on Earth, then de facto you have to be treated as if you are, right? De facto, right? So that's all that we have to conclude about them. They really do mean it. They really do mean to destroy all life on Earth. They're going out of their way to justify it and engineer it while pretending environmental virtue. They're just pretending, right? It's all bullshit. Here's an interesting thing to think about. Put yourself in sci-fi mode. Think of put yourself in just a mode of viewing something remote and forlorn and kind of beauteous but disturbing. So has the Kepler Space Telescope discovered an alien megastructure? So the story of this is that the Kepler Space Telescope was looking at a whole bunch of stars, like millions of different stars, looking for signals in the star's light to see if it indicated planets going in front of the stars. But there's this one star that they found, and the light dips of the signal made no sense at all. And I've looked at it too. I'm an astronomer, as you guys know, astrophysicist. The light dips, they're not freaking normal. Like there's no explanation. Like it's not from a it couldn't be from a planet passing in front of the star. It couldn't be any natural property of the star. It's just a completely artificial looking signal, right? And so, they've said, is it evidence of an alien megastructure? So consider this. Consider that what we're seeing there is a derelict artifact of some long lost civilization that's now, and this thing is now floating around in front of this star, randomly occluding this star's light, giving this weird signal that we see from it sometimes. And it's out there derelict, and it's floating in front of this world that used to be there, used to have life on it. And now it's moon barren and dead, right? Imagine that, right? That could be what we're seeing because, and I kind of explain, I mean, I don't want to get too much into the details here, uh, but, there could be a force out there that does that to worlds. It goes through the galaxy, destroying worlds by infiltrating the population and getting them to frickin' build these things to destroy themselves. So imagine that this happened on some other planet. Who lived there? Who lived there? It would have been a people like what? Like us. They would have been a lot like us. Very industrious. They were able to build a frickin' solar umbrella. Something that we maybe could do, right? But they were very trusting. They were naive. They were too easily frightened. They got frightened by the weather too easily, by the story that this force comes in uh, with these stories, right? They're too young in consciousness, just like us, like children, way too innocent. And they were intellectually raped to death, right? With this gaslighting, with this sort of gaslighting, right? This is all gaslighting up here that I'm getting in response, right? It's gaslighting. What's gaslighting? Gaslighting is a way to get, it's harassment. Gaslighting is harassment, and it's a way to get a person to question their reality. So these people were gaslighted and intellectually raped to death to the point that they frickin' build a solar sail and destroy themselves. And there's references to, well, I mean, yeah, I mean, there's anything in fiction. Sure, a reference in fiction doesn't count for much, but maybe that's what we're looking at. Profound, right? And now that force is here. It did it there, and it's that planet that used to be there with people that were probably a lot like us, just put it in some fiction terms. Maybe it was like that, right? They're freaking dead and long gone. And now it's happening here to us. I don't know, something to think about. You just kind of have that conclusion because these gaslighting comments are so impossible. It's impossible. How is it possible that a PhDs in physics, across time and space from all these different journals, from all these different universities of climate science I've tried talking to over the years, a lot of you have been with me for, a decade and more doing this, right? How can a physicist tell me, how can he say to me that he cannot communicate his level of disrespect for me because my spherical model is so dangerously ill-informed? That's not, and all the rest of this stuff, right? Like, I don't know, for me, it's just you got to realize the impossibility of this. Well, I mean, I go to some pretty unique places because I pursued this to the end. I pursued this to the very end in Planet, in Planet Wars. You guys should read it. Pretty fun. Okay. All right. So these people aren't stopping. They aren't going to stop. And my videos and books don't matter to these psychopaths who obviously, now it seems pretty obvious, want to destroy life on Earth. They don't care. Uh, what's interesting is how resistant they are to physics solutions, right? It's telling, isn't it? They're strangely, totally resistant. They're so afraid of this problem, right? Oh, they're so afraid of climate change. Wouldn't it be great if you could just show that it doesn't exist? Oh God, what a load off my shoulders, off all of our shoulders. Wow, we just did the math wrong. Oh, and it's pretty easy to understand how we did it wrong. But man, they do not, not want to go there. They don't want that solution. The solution they want is the solar radiation management, is blocking out the sun. The solution they want is carbon capture and storage, sucking carbon dioxide of the atmosphere, right? And stratospheric geoengineering, blotting out the sun with, um, spraying stuff in the stratosphere with jetliners and whatnot, right? So they're really, really, really resistant to just doing the basic physics on that and reevaluating. But they really, really want to do this other stuff. It's a bit telling, don't you think, right? It kind of gives the plot away. So yeah, I mean, if you guys aren't aware yet, I've lost my career, right? I'm no longer working. They said that my books were, harassment. Of course, they can harass me all they want with gaslighting and telling me these things that they have such levels of disrespect for me. They can gaslight you all the hell they want. I mean, it's just power. It's nothing about evenness. It's nothing about fair play. It's nothing about free speech and let's have a honest debate. They have the power. They have the power right now. They can say that I'm a harasser because I say that the earth is round and not flat, right? And they can, um, not let me work anymore. So yeah, basically I'm not working anymore. I've lost my career. And yeah, because I point out what their plans are, right? Yeah, so we are apparently in the situation where we need to defend planet Earth from a well-coordinated effort to end our biological template of photosynthesis. Yeah, I mean, wow, did we ever come some distance to get to that? But it's that's the rule. That's how it works in law, right? It's called de facto, right? If you act like you're the one doing something, then you are the one doing something, or it works some way like that, right? So if they're acting like they are planning with lies and stupidity and gaslighting and what they damn well know should be some better physics that I can show to them, they're damn well ignoring that and they really want to do this other stuff instead, well then de facto they are equivalent to um, some sort of force that wants to destroy all life on Earth, right? That's just, and the target is photosynthesis. The target is carbon dioxide and sunlight, right? That's the basis of photosynthesis. They're targeting specifically carbon dioxide and sunlight. Why would you target that? That is what you would target if you wanted to end a planet's life, right? If you came to Earth and you said, I want to destroy all life there. Well, number one, what's the chemical basis? What's the energetic chemical basis? The first chemical is carbon dioxide. That's the first chemical. That's where all life starts, is the chemical of CO2, and then it goes from there. And then the energy source for that is sunlight. You target those two things, and uh, and that's how you would, you remove those things from the earth, and that would be how you end all life on Earth. And they are de facto acting like that's what they want to do, right? So you have to treat it like that's what they're doing, because it really seems like that's what they're doing. Okay. Yeah, here's an interesting quote. I mean, just to speculate for fun a little bit more, I just want to think about this. JFK, remember JFK, that president who was shot? This is just an interesting quote, and I'll give some context after. What did he say? For we are opposed around the world by a monolithic and ruthless conspiracy that relies on covert means for expanding its sphere of influence, on infiltration instead of invasion, on subversion instead of elections, on intimidation instead of free choice, guerrillas by night instead of armies by day. It is a system which has conscripted vast human and material resources into the building of a tightly knit, highly efficient machine that combines military, diplomatic, intelligence, economic, scientific, and political operations. Its preparations are concealed, not published. Its mistakes are buried, not headlined. Its dissenters are silenced, not praised. No expenditure is questioned. No rumor is printed. No secret revealed. The question I have for you guys is, still on? Yep, good. Who the frig was he talking about? Who was JFK talking about? Because you know what, he actually wasn't talking about the Russians and the communists here. Um, I'll make the point here. Us regular humans, we're not capable of that degree of command and control because JFK is the president of the United States. Especially at this time, was by far and away at that time in the 60s, the world leader in power in scientific technological development. And he's talking about what seems to be a military operation that's just like blowing his frickin' mind, right? So in the context of him being the president and at the head of the human abilities of the most powerful military in the world and their abilities for command and control, he's like, we're facing something that has frickin' command and control abilities that's frickin' way beyond what we can frickin' imagine. What the hell is he talking about? He's a leader of the most powerful country military on earth. He's not referring to communism or Russia here, and he's overwhelmed by what he's facing. What the hell could it be? Well, maybe it's the same thing that I've discovered and written about in Planet Wars. Anyway, guys, if you want to support me, I mean, I hate doing this. I don't like asking people for money, but just I've never felt right. But this is what people do. Whatever. If you want to support me for the time being, you can either use PayPal, PayPal /Joe Postma. I also have this Give, Send, Go for ontological mathematics, where what I want to do, so that's just I mean, so givesendgo.com/ontological mathematics. So I talk about some experiments that I wanted to do there for ontological mathematics and illuminism. But really what I want to do too is develop a school. We need a new school where we teach critical thinking. Imagine teaching children how to critically think about the difference between that flat Earth model and the spherical Earth model. Could you imagine teaching critical thinking with that comparison? God, wouldn't that be so great? That'd be so great for education for children, right? That's what I really want to do. I want to build a new curriculum model for for children, right? For school, for everyone, for everybody, right? Would that be awesome for all of us? Because what's happening right now are people are freaking insane. I mean, our school system is obviously retarded, ridiculous. It's all in my Planet Wars book where I describe and uh, and critique what's wrong with our whole education system, right? It's all just become such a joke. I mean, people are literally being made retarded. They're being made retarded through our what has become of our curriculum in the West, right? So I want to completely go back and create a new model for a curriculum, right? That would teach critical thinking and proper science and all that, right? Would that be fun? That'd be great. We're getting really needed, I think. Okay. You can also buy my books if you want, right? So here's my 5 books. There's a Planet Wars. That's just my author. Yeah, so just links here. This will be in the PDF, right? That you can download after. Looks like the last slide. Yeah. So that was my first book. I wasn't really cottoned on yet to the full scale of what I was facing. Here was building up more, and in between this book and this book, I describe what I did in the time interim to finally realize that this is not just accidental stupidity. This really is purposeful what they're doing because you can't you know what I was saying before about all those gaslighting comments. And so, yeah, Planet Wars is really a profound book. It'll blow your mind. Still blows my mind when I read it. And then Illuminism, this gets into, you know, we need a whole new sort of culture, religion, whole new way sort of doing things. You know, I summarized the answer to existence, basically a religious outlook. And you know what's great? One thing that I left out, and damn, I should have put that in Illuminism, was the Greeks and their form of the good and how Pythagoras and Plato, do you know what, so Pythagoras, it's with Pythagoras with the Greeks, at least I've read this a bunch of times, who had some idea that he could reason, and of course ontological mathematics and Illuminism was all about this anyway, about the existence of the soul, that we real humans have a soul, right? And the soul is a real thing that actually exists, and we can now describe it mathematically and obviously, you know, this idea doesn't fit into scientific materialism, but look at the scientific materialists. They're flat earthers that are planning on destroying the world. I mean, yeah, there's sufficient reason to not be a scientific materialist anymore, just on that. Um, but here's the really beautiful thing. They said that it was the reasoning part of your soul which is immortal. Now, talk about what is religion about? Religion is about your soul, and it's about how you continue after death. And the Greeks said that it was the reasoning part of your soul which survives death. Is that great? Talk about a basis for a religion for smart people, right? Not scientists. They're not smart people. They're scientific materialist idiots that, you know, give me these comments. In my Planet Wars book, I basically show that they're not people. They're actually not people. They're either NPCs, they're robots. They seem to be spiritual computer programs, which aren't. They're like, what do you call that? The Oh, it's from tip of my tongue. Golems. They're golems, right? They're golems. You know that spiritual rhythm from the Hebrews or whatever. The idea of a golem. They're soulless. They actually don't have a soul. They're not real people. Um, yeah, and that's what we're facing basically. So anyway, but for those of us who do have real souls and who can rationally think, Yeah, the reasoning part of us is the part of us that's immortal. So talk about a wonderful basis for a religion. So that's what I kind of do in Illuminism. And then, yeah, the simultaneity paradox is just showing how where science started going wrong. And it's kind of throughout all my books, talking about how science goes wrong. But anyway, that's good. If you haven't read my books yet, you can pick those up. Okay, so that's it. Finally done, and I'll switch back now to the live chat and see if you guys want to keep chatting or what. Look at that, 2 hours on the dot. I figured it'd be about that. Whew. See up here, Carly O'Connor says they're the antithesis. Yeah, actually, you know what I actually identify them. I classify them biologically, well, noetically, meaning of the mind. I classify them as what kind of species they are. They're a parasite. They're a parasitical species, actually. And well, I get into some more details and explain what they're doing here in that book. Yeah, exactly. Walks like a duck. Yeah, exactly. If it walks like a duck, it is a duck. Um, yeah, Carrie said we need to stop farming. Yeah, absolute gaslighting. Exactly, right? If truth was respected and appreciated, none of us would be here needing this and us. Yeah, exactly. Yeah. Um, Boomy, interesting thought. That was probably to my comment about that sunshade thing. Yeah, alien civilization that got screwed, got wrecked. There must be scientists who knows Joe's analysis is correct. Yeah, I know that's weird, right? You would think I would be able to find, right? That's the freaking weird thing about it. It's so freaking well coordinated. Like I submitted that paper trying to talk about this to so many different journals around the world, and I got all these responses. I was like, this is so freaking well coordinated. Like it's literally no, like it's literally been impossible for me to find a scientist who can think about this and just frickin' look. And like I said, and people have set up, Boomy and other people. I think have found people for me to debate, and I've had it on online before, and they're just like, no, nope, I'm not going to look at your model. No, don't even put it on. I'm not going to look at it. Like they just cannot frickin' look at it. They refuse to. Um, Dark forces. Yep. Um, Humankind is 300,000 years old. We're domesticated and controlled people. Yeah. Work on building trust. Dams and gatekeepers, yeah. The antithesis, yeah. Your mission, my mission in life has just begun, maybe, yeah. Pandora's box opens, yeah. Yeah, he was referencing covert domestic communist starting point, but as we know, these academics and labor organizers worked with industrialists and wealth, yeah. Need to talk to Peterson, yeah, maybe, yeah, it could be idea online university or something. Um, Love to work for you, Joe. We could, yeah, wouldn't that be great? Exactly. That's the thing, right? That's what I've always said. There has got to be a huge, like, think of all this woke stuff. Parents don't want their freaking children being exposed to woke. I mean, they don't. I mean, yeah, I mean, sure they give you that impression on the news that it's also cool and all parents want to do, but no. If you're a parent of a child, as I am, no parent wants all this woke freaking shit talk to their kids. They especially don't want their kids being taught to freaking, sterilize themselves and do all this uh, transgender stuff. Like God, no one freaking wants that, and that's so universal out there now. It's inescapable. It's everywhere. So what there is a huge market demand for a real, safe, proper, normal, healthy form of the good following school system. Could you imagine the demand for that? It's like such a freaking untapped market, and I'm just like, yeah, I have a, I don't have it here, but I basically have the outline all written out. I have the outline written out, and I'm like, well, should I publish it? Well, if I publish it, someone else will take it. Blah, blah. But if I had frickin', I don't know how much funding I need, but yeah, like it's there, ready, and lots of good people who would want safe, healthy, normal education for their children, right? Yeah, and especially the homeschoolers. Yeah, exactly. Um, okay, Carly, cool. Yeah, large number could be persuaded. Well, they need the TV to tell them or something. I don't know, right? Good presentation. Thanks, Boomy. Parasitic, yes. Yeah, yeah, you're right. Yeah, large people don't buy it, and it is growing every day. But imagine, like that's what I've been tr working on this for so long now. I mean, this is now at such a point that this is so explosive. Imagine if this got out en masse and people truly understood what was done and how it was all done, right? With this flat Earth bullshit. Like literally, it's literally what it reduces to. It literally reduces to they tried to work out some physics for flat Earth theory, right? That's literally what it reduces to. Imagine how explosive that would be. How revolutionary. I mean, that would be so good. It would be good for everybody because it would, of course, they're horrified by it because they're all like, oh, I'd lose my position of, you know, tenure or what is it? No, status in society. People would think that we're stupid. Well, eat it up, Buttercup, because you know what? It's freaking going to be way better for everyone else in the end anyway, right? And it's going to be good for evolution, good for everything, mental evolution, everything. Um, what about the lukewarm skeptics and their obsessive defense? Yeah, that was a big thing that we fought with. And I should actually reference the group. I should have had a thanks at the end to this Slayer group and what has become Principia Scientific International. That's who really started me on this. And I've developed this as fully maximally as I could. Principia Scientific International does a bunch of other stuff now. They still do this too, but I've really focused on this and really pursued it to its very end and have found, yeah, some really profound and amazing and awesome science about it, right? And lies and whatnot. But yeah, so the lukewarm skeptic thing, they're controlled opposition. They seem to be the NPCs too. They're also golems, soulless golems or something, and they're programmed. Yeah, it was just actually I sent this the invitation of this to Roy Spencer, and yeah, just some retarded freaking comments back from him. I'm like, Roy, and his in this email, I'm like, Roy, don't you think it's valuable to say and think about the sun being 121 degrees Celsius input versus saying it's minus 18 C? Why don't you think that's relevant to talk about? And he's just like, you don't understand a planar geometry cartoon. And I'm like, you just get these retarded frickin' comments, right? So yeah, it's gatekeepers and it's imposters and they're just part of the controlled opposition forces. Yeah, exactly. These fake skeptics. Yeah, they were worse anyway. Well, they're all bad, right? Yeah, exactly. Yeah, thanks, Malaby. Have courage. Thanks. The demand is huge. Yep. As a mom to three, so concerned about the kids being influenced by two. In a way, I've been patient and let the irrational take its own graves, knowing they inevitable. Yeah, they would, but they're going to hurt a lot of kids. They're hurting a lot of kids on the way down. And so, yeah, you got to take your kids out of that system. Um, okay, cool. All right. Well, you guys want to stay on? Let me know. No worries, Lee. It'll be up for rewatching later. After. I think it'll be up there right away, right? But no, it's time to generalize or to synergize and actualize. Yeah, 2 hours is good. Boom. Yeah. I keep thinking we're here to help the 99%, so you need to work with them too. All right, yeah. Yeah, Boomy, you're right. It's late. If you guys are all good, I'm good. So this will stay online. This whole thing can be watched. The first bit is how to do it and prove that there's a way to do it without the greenhouse effect, and it's a basic, physics class, how you do it in physics class, right? Okay, awesome, Phil. Glad you liked it. Oh God, yeah, no, I've done that so many times. The green plate thing is just it's just the same greenhouse effect thing, which just comes from a flat Earth. It's just fake physics. I've done that on my blog tons of times. I think maybe in my YouTube. I think I've done it in my Planet Wars book too. Yeah, it's just stupid bullshit. It's still just the fiction of the radiative greenhouse effect, fiction, which comes from flat Earth theory, and then they just try to say, well, let's think of a green plate. And it's like, okay, you're still saying that heat flows from cold to hot. And they're like, well, it does because the laws of heat flow don't apply to radiation. That's like that. That's just there. There is no textbook in the. There's probably thousands, hundreds, maybe, or maybe thousands of thermodynamics textbooks in the world. Not a single one of which says that the laws of thermodynamics don't apply to radiation, or that radiation is exempt from them. That simply it does not exist. So that's what they say. Um, okay, thanks, Louis. Glad you liked it. Good. GCP 2098. Nice. Joe Poe, good. Yeah, working heat shield backwards. Yeah, that we're doing. Yeah, Khan Academy. Can you learn calculus there? Yeah, for sure. Totally. Oh, 5 a.m. Wow, Philip. Awesome. Okay, well, if we're wrapping up, I'll just give a couple more minutes for wrap up and then, yeah, get going. See if any other comments come in to respond to. If not, it's 10:07 here, so I'll give it to, say, 10:10. Okay, 3 more minutes. Thanks, Lee. Thanks, guys. Thanks for that, K. Protect 1024. Thanks. Thanks, Malabi. Love you too. Yeah, it'll be posted. Should be right up there, Ken, in the live stream. Should be right there. It's also on my blog. The live stream should automatically be there right away. If it's not, it should be recorded. Yeah, no, it'll be there under live. It'll be there under the live stream or live tab in your on my YouTube channel. Definitely will be there. Good night, Boomy. Thanks, Philip. Yeah, good night, Philip. Okay, guys, there we are, 10:10. That's it. That was fun. Thanks, everyone. Gonna stop the stream. Bye. Thanks, everyone, so much. Take care.